So I would like to thank the committee for giving us this opportunity of presenting our work here in this conference. So as you see, my talk will be about experimental observation of high-line Rydberg states which are survived from a strong field interaction. This research was done in the Photonic Institute of Vienna University of Technology and will be continued in future in cooperation with the Institute for Theoretical Physics. So as you already know, a Rydberg state is a state with a large principal quantum number. So it is actually predicted in the Bohr's original paper on hydrogen, but not discovered for a long time in laboratory. For the first time, the experimental measurement on Rydberg state from strong field interaction was done in Max Born Institute in Berlin on the work of frustrated tunneling ionization, also in the works of Professor Gang and Professor Biggers. They use the Rydberg state to explain the low energy and zero energy structure in photoelectron spectra. There are lots of applications one can name for these Rydberg atoms and Rydberg states. So, for example, you can say that they are really sensitive to the electric field, the ionization of these states. So one can use them to precisely measure the electric field, or because of their big size and their interaction between each other, one can use them as a switch to control the other atom or to switch each other. So which is really useful in quantum information and quantum computation. Also, a few days ago, Professor Harosh here talked about using the Rydberg atom to counting single photons and also probing the Schrödinger cast of light. So having Rydberg atoms is a very powerful tool for many applications. So we can explain the formation of this Rydberg state from this famous three-step model. You know that in the absence of electric field, electrons are in ground state, exposed to a strong field of laser pulse. Then the electrons can tunnel through the potential barrier and get ionized. Then they can accelerate it and oscillate in the external laser field until the laser pulse has passed. Afterwards, if the kinetic energy of the electron is lower or smaller than the Coulomb potential, they can recapture to the parent ion into some Rydberg state with a large quantum number. Now, these electrons in this Rydberg state, since they have a very small ionization potential, they can easily get ionized by very weak DC field, DC electric field. So our work will be measuring the ionization from high-lying Rydberg state with a very small or very weak DC electric field. So in the experiment, we take advantage of the Coulthard's technique. Most of you know about it. So first, the laser pulses of the duration of 25 femtoseconds are generated from a standard titanium sapphire amplifier system. The system has a repetition rate of 5 kilohertz with a center of wavelengths of 800 nanometer. Then these laser pulses are guided into a reaction to a chamber, vacuum chamber, which are focused onto a cold supersonic jet of molecule. We employ the reaction microscope technique to do the coincidence measurement of electrons and ions, which comes from the interaction of laser field with the atoms and molecules, and also with the data that we got from the position and the time of flight in these two detectors, which are MCP detectors. We can retrieve also the momentum distribution of these charged particles. We used the laser pulse of the intensity in order of 10 to 14 watt per centimeter square, and also the peak field strength for us was around 1.4 times 10 to 9 volt per centimeter. And as you see here, an electric field is actually in Coulthard's technique used to collect the charged particle into their corresponding detector. The upper detector is for electron, lower for the ion. And you see that we had the maximum electric field of 30 volt per centimeter. Actually, in our case, now it is used to ionize the electrons from these Rydberg states. And you see the effect of electric field like that. So here you can see the photoion photoelectron coincidence spectrum, which we get from our measurement. In the Icpeac spectrum, one can study the correlation between the time of flight of ion and electron, which hit the detectors in the cold streams after the strong field interaction with the laser. So you can see, for example, here the correlation line for the argon plus and an electron and argon double plus with an electron, and you see actually this line, this correlation exists for a very long time, up to several microseconds. We now just we will focus on the single plus data, and if we zoom in this part of the spectrum, we can distinguish two different regions. One is the ionization signal from the laser interaction, and the long tail of correlation, which is the ionization signal from the ionization of this highline Rydberg state. So in our analysis, we separate these two parts and get the information about the Rydberg state from this part, which happens long after the laser interaction. In most cases, for the comparison and also for seeing the effect of the parameters on this process, on this ionization from highline Rydberg state, we find a lifetime and check the results. So we start now with our experimental results. So as I said, there are these ionization from these Rydberg states is really strongly dependent to the electric field. So our first evidence for this process would be to show this dependence. So as you see here, you can see the clear dependence of the electric field of the lifetime of the excited hydrogen molecule. We performed our experiment for 3 different electric fields, and you see that with increasing the electric field, the decay rate will be faster. Actually, in each measurement, the yield of the ionization, ionization signal is normalized to the ionization signal of the laser interaction part. So we also performed the measurement with the DC electric field of 0.1 volt per centimeter, which is actually correspond to the over-barrier ionization of the highline Rydberg state with principal quantum number bigger than 238, which is a really big number. Then we also investigated the effect of laser pulse intensity. You see here that we perform our measurement for one molecule and one atom for different intensity with the same electric field. And you see that there is no dependence on the laser intensity. We expected also that because this ionization happens long after the laser interaction. To confirm this recapturing mechanism, we also measured the dependence of this process on the electricity of the laser. You know that for the recapturing mechanism for the electron to get recaptured to a parent ion, the final kinetic energy or final momentum of electron has to be very small. And this actually, in the case of tiny electron, it depends on the initial vector potential. With increasing the ellipticity of the laser pulse, the vector potential on the plane of the polarization change from a line to a circle, which gives the momentum of electron far away from the zero momentum. So, and prevent the recapturing mechanism. And you see also here we measured the ratio of the argon plus, which comes from ionization of Rydberg state, to the argon plus, which comes from the laser interaction, and it's strongly suppressed by the increasing the ellipticity of the laser pulse. For having some ideas about this highline Rydberg state, we analyzed the lifetime of excited argon atom in this electric field, and we noticed that different part of this lifetime actually has a different slope, so different decay rate. We fitted each part with the exponential function. This is logarithmic scale. So, and we found the decay rate and mean lifetime of the corresponding excited state, and you see here with different numbers for the mean lifetime. So different decay rates, we know that actually indicate that different highline Rydberg states are involved in this process. We also retrieved the perpendicular momentum distribution of electron from this process, from ionization from Rydberg state, as you see in the blue line, and by comparing that with the perpendicular momentum distribution of the electron from the laser interaction part, we can compare these two, and you see that they have a quite different full width at half maximum for these two distribution. To prove actually our observation, we did our measurement with different atoms and molecules. We actually observed this process. Actually, the process means this long tail of correlation in the Icpeac spectrum. For all the atoms we did the measurement with, so neon, argon, helium, and small molecules like hydrogen, acetylene, ethylene. But we didn't observe actually this process in bigger molecules like butadiene or hexane. And actually this comes from this instability of these bigger molecules in highly excited state, because then they result in the molecular fragmentation and dissociation before the reionization. And we also compared three different targets: hydrogen molecule, neon, and argon, and they have some different. Still, we are working on this data. We are not sure about it, but for having some explanation that we know that because of the orbit of this accelerated electron is so big, so the shape of the potential is not that important in this difference, and we believe that this difference comes from the tunneling ionization step in this three-step model, which the orbital of the electron and its shape is really important in ionization process. So with this slide, actually, I finished my talk, and as a small summary, we experimentally observed this weak DC electric field of ionization of high-lying Rydberg state. We then investigated the effect of intensity, laser pulse ellipticity, and also the effect of DC electric field on this process. And finally, our observation shows or indicate that different high-lying Rydberg states are populated during the recapturing of electron to the parenchyma. Thank you for your attention. I'm open to your questions.